So our last chapter was about rotation, right? So things rotating, okay? And our previous discussions before that have been about translational motion, okay? And then to start off this chapter, we're going to look at what happens when we put those two things together. Well, if you have something rotating and translating at the same time, one form of that is rolling, okay? So like if you have something that's kind of rolling along on the ground, that's what we're looking at. Okay, so rotation plus translation is rolling, at least in this circumstance. Okay, so we're going to look at just a couple quick examples in this one. So the first thing I want to look at is this. Okay, so if you take an object that's rotating, alright, that would mean its center of mass is at rest, it's stationary, and it's traveling with a velocity here, same velocity, opposite direction here. If you apply to this rotating object translation, so basically give a velocity vector at each of these points, okay, then all of these are going to add, and so this and this are going to add to be 0. This is going to add to be that, and these two together will add to be this, okay? And this is what happens when we have rolling motion, okay? So you might look at the object and see the object overall moving with this velocity. If you're just to look at something, this object that's rolling, if you're just to look at its rotation, look like this. When we put those two things together, we get this, okay? And there's a couple important things to think about here. The first thing, at the point of contact with the ground or whatever surface it's rolling along, at the point that's at contact is stationary. It's not moving at that instant, okay? The center of mass of the object rolling is moving with the same velocity as the translational velocity of the object. And then this object up here, or this piece up here at the very top, is going to have twice the velocity of the center of mass. Okay, the piece up here is moving twice as fast as the center. Okay, so if we look at this image of a bike wheel here, you can notice that at this point at the very bottom, it's not very blurry, okay, and this is that point where it's stationary. It's fairly blurry here in the middle, and then it's very blurry here at the top, where it's moving twice as fast than it's moving here, and then here it's stationary, okay, and this is for objects that are rolling, okay, and the key in this chapter is that the object's going to be rolling without slipping. Okay. If objects are slipping, then all the stuff that we are talking about doesn't really apply. And so to make sense of these things, we have to kind of assume that they're not slipping. Okay, I just want to give further evidence of kind of the velocities of each point in the wheel. This is another technique for analyzing rotation. So in the previous example, we looked at it rotating about its center of mass. Okay, for this example, we're going to look at it as if it's rotating about the point where it's touching the ground. Okay, so there's going to be some omega about this point. Okay, some angular velocity about this point. And the point that it's about will change at every instant. It'll always be the same angular velocity around the point. And so each of these positions on the wheel has the same angular velocity about this point. But since each of these spots on the wheel has a different radius, okay, they're going to have a different velocity. Okay, so since the distance from the bottom to the top is 2 times r, then we get twice the velocity than we would to this point here at the center of mass, where it's just 1 radius wr. And that means that here at the bottom, okay, where we have a radius of 0, we get a velocity of 0. Okay? Okay, so here's a fairly complex question that kind of involves what we're discussing about rolling. So we have a bicycle with one wheel that is basically twice the size of this other wheel. Okay, so let's say that this is h. We'll call this 2h. All right, and this is bicycle. So it's moving along. All right, we'll just make a little bicycle here. You can see this is a pretty awesome drawing of a bicycle. So anyway, it's rolling along, and the question is, when the bicycle is moving, is the linear speed at the very top of the rear wheel greater than, less than, or the same as that of the very top of the front wheel? Okay, well, what do you think? And what do you think about the angular speed? Greater than, less than, or the same as the front wheel? Okay. Go ahead and submit your answers real quick. All right, so let's think about it this way. Would it be possible for the edge of this wheel to be moving across the ground faster than this one? Wouldn't they have to be the same in order for them to be rolling together? Okay, so what that means is that the linear velocity for both wheels is the same. Okay, because of the fact that they're traveling along at the same speed, they're moving on the ground at the same speed. Okay, well, if that means that v is the same at the top for both of these. Okay, well, if v is equal to omega r, then v over r equals omega. That means that omega is bigger for this one. This one's going to have a faster angular speed because the radius is smaller, which means that this wheel, if you're just looking at the rotational aspect of it, this wheel is rotating at a lower speed than this wheel. Okay, but they both have the same linear velocity on the outsides of the wheels.